Cool. All right, thanks everyone for waiting. I'll make that 5 o'clock in the UK, so I guess we're just about ready to get started. So welcome to the Neo4j online meetup. So today we've got Dan, who's going to be talking to us about a project that he's been building called Graph NLU. So this is about natural language understanding with Python and Neo4j. So I came across Dan's project on one of my searches of Neo4j repositories on GitHub. Only a bit of housekeeping. If you're struggling to see the text on the slides, you probably want to change your resolution on YouTube. So bottom right-hand side of your control, set that to 720p if you're struggling to see. And if you've got any questions, put them in the chat on the right-hand side, and I will collect them and ask them to Dan. And with that, Dan, I guess I'll hand over to you.
All right, thank you. So I'll talk a little bit about a project that I've been working on called Graph NLU. My name is Dan Kondratyuk, and let's get to it. So a little bit of a summary before we go into it. A little bit about me, a research question that has been motivating me these past few months, my experiences working with Neo4j, and finally the natural language implementation. I'll go into a Python notebook that will basically show you all the code that working on and a little bit about how it works. A little bit about me. I am a researcher and developer, and I recently graduated with a bachelor's in computer science at Boise State University in Idaho. I'm a member of the Speech, Language, and Interactive Machines, or SLIM, at Boise State. Essentially, the best way I can describe it is it's the intersection between interaction and computation. So we have several undergraduates and graduates there working on various different things like automatic speech recognition, natural language processing, robotics, stuff like that. And we're really interested in doing research about this kind of stuff. So that's where I'm at and kind of what's motivating me behind what I do. So a little bit more about me. I'm also a full stack developer for a product called Hello Augie. Essentially, it's a personal assistant that remembers when you forget, so it can remember a whole bunch of different relationships about things. So say you forgot someone's name and you want to ask the system about it. Provided that you put that information in there in the first place, you can ask, hey, who's that person that I met last week? And he knows my friend named Matt, and the system will be able to look at the different relationships and try to figure out what person you're talking about. So if we have time, I can demo it a little bit about how it works. So we have a landing page. It's not quite done yet, but it's there. So that's enough about that. Let's get into the motivating research question. So I've been working and studying with intelligent personal assistants, so like Cortana, Siri, Alexa, Assistant. They're all assistants that you can talk to. They translate your speech into text, and then they reason about it and perform some kind of task. But they have some notable memory problems. They commonly behave like amnesiacs, so at least I've noticed. Their memory can be quite inflexible or perhaps non-existent, and interactivity is limited to predefined knowledge and known tasks. So here's one example with Siri. Hey, remind me to this weekend to install the car seat. Okay, I'll remind you to install the car seat. When would you like to be reminded? Saturday. Okay, just tell me what you'd like to be reminded about. What? Okay, I'll remind you what? At 9 a.m. So we have a little ways to go before we have assistants that can actually remember what you're saying and dynamically interpret and update what the state of the conversation is. Right now, they're just limited to these little predefined tasks, which are quite useful, but could be better. So motivating me throughout all this research is the questions: how could interaction be stored in memory, and how can that information be leveraged for further use? So I've come to the conclusion that real-world information is highly relational, and there's lots and lots of different ways you can organize information in various different ways, and really want a framework that is flexible. And there's no better data structure than a graph to represent such a thing. The major goals with this project is we want to create a system that is both dynamic and interpretable. So going into experiences with Neo4j, we thought of first having a graph of the various relationships between things, where we have on the left this little graph in memory, and we want to persist our graph to some storage over the long term, because we want to be able to ask the system maybe a week later, maybe months later. So we want to persist this information across a disk. And the first I thought about was maybe we could use a relational database. It requires some kind of mapping function. We have the square in the middle, and it basically transforms this graph into and flattens it out into a bunch of rows into a relational database. I decided not to take this approach because for two reasons. One, it's a lot of work, and it's a bit cumbersome to, once you update the graph, you not only have to update the database that represents those relationships, you also have to update your middleware that basically shuffles data between the database and your memory. So decided maybe there's a better way where we can represent data, the graph, both in memory and in our persistent data. And the second reason why we chose this is it also fundamentally changes how you think about how you organize that data. So by flattening it out into these rows into a relational database, you're kind of thinking about it in a different way. And that's going to change how you build your graph in the first place. So we thought maybe we could find something that can represent this, as we have it, and not need to deal with a bunch of configuration and issues with mismatched data. So we looked into a few different technologies and decided to land upon Neo4j. And reason why is we wanted, again, persistent storage that represents the null problem domain. And we found that it's quite excellent for ad hoc relationships, and it's very flexible and has quite, at least when I was working on, quite intuitive syntax. And I was working on it for a few months now, and decided to continue on with I kind of like it, and decided to integrate this into the project. And also it has quite efficient querying capabilities, and really wanted to utilize this in the project. So let's get into the natural language implementation. So one use case one milestone that we really want to get into natural language, basically to use it as a natural language database. So we have a statement, and we want to update our internal knowledge. And say we have some kind of natural language statement that says, John's email is john@example.com. So we have, this statement, and we want to extract it into a data frame that says, this is a statement with a name of John and an email of john@example.com. So then we transform this into some kind of internal graph representation we have on the right. And then the second part is, given a natural language question, we want to retrieve those results. So we ask a question, maybe, what is John's email again? Question with the name John. We ask about the email, and we want a pattern match on this internal representation. and basically retrieve those results. And we get back John at example.com. So that's like the really first milestone that we want to get into. And for this, we looked at several different corpora that can suit our needs. We found one that almost matches what we're trying to do, which is the Facebook Babby tasks QA questions 1 through 20. And basically it's structured into different tasks, and they're basically toy problems that are organized according to several statements, like in this first task, John traveled to the hallway. Mary journeyed to the bathroom. Where is John? And the answer is in the hallway. John traveled to the hallway. That corresponds to the answer to that question. So the goal is to, given all these statements, answer the question correctly. So the steps that I took, and it's in the Python implementation into a Python notebook, is to tokenize part of speech tag and produce these subject relation object triples. And then the second step is to merge all these triples into a single graph, and then answer each question using the graph and compute the accuracy. So once we step through the Python notebook, it'll be a little bit clearer as to why I did this. But that's just a summary. So briefly, the results before we get into the nitty-gritty in the code. Accuracy, but of course, the data is very simple. It should be absolutely no surprise that we can do this, because it's quite easy to get to that level. And it's a synthetic data set, so as well, so it's generated by a computer, so that's that. But not only that, this system allows for more complicated questions like what rooms has a person been in, and how many times has a person changed rooms, and how many times has a room been visited. So using this system where we have this internal graph and we create this knowledge of all the syntax, query it, we can answer a bunch more questions than what we had originally built the system for. And this is really nice. So in the future, I'd like to use more machine learning in the system to actually extract the frame, and we'll see how it works. All right, let's get into the notebook.
Maybe zoom it in a little bit down so people can see it. A bit small.
Oh yeah, I think I should expand it.
Cool. If you have any questions about the introduction, just type them on the chat on the right-hand side, and I'll send them to Dan. I guess probably everyone seems okay so far.
Okay, cool. Good. Maybe I can expand this some more.
Yeah, maybe.
All right, can you see that?
Yeah, I think it's good. Shout if it's not.
Okay, so this repository is on GitHub. You can look at it. It's called Graph NLU. If you Google it, graph-NLU, you'll be able to find it. So kind of explain the background to why want to do this project in the first place, and a little bit about the data set we're using. So hopefully we won't run into any errors. I've already tested this beforehand. So we import, we're using Pandas library to basically organize our data in this format. It basically allows you to easily munge your data and gives you a really nice way to basically process your data. So we're using QA1, which is the first task we saw in the slides. We have, let's execute this. import our data into the data frame, display it. So we have Mary moved to the bathroom, John went to the hallway, where is Mary? So we have this problem domain set up. Next, we do a little bit of light processing. So we tag our sentences based on whether it's a statement or a question. So if we execute this, we have this new column, S for statement and Q for question. And we also tokenize the sentences using NLTK, Natural Language Processing Toolkit. And basically, we transform this sentence from a single string into an array of words.
So is NLTK, is that a Python library that you're using there?
Yes,
yeah.
Using.
Okay.
There's a bunch of others. This is the one that I learned about in class, so I'm using it here. It's pretty simple to set up. You have to download a little bit, little thing right here to get it working, but I found it pretty easy to work with, and they have a book, entire book dedicated on it.
Oh, cool. So there's lots
so
of examples to copy if you get stuck.
Yes, if you want to learn more about how this works and what it's using underneath the hood, then you can refer to those examples.
Cool.
We tokenize this sentence, split it up based on white space and a few other rules, and continue on. So here I define a couple functions that will basically display just the statements and just the questions. So if I execute this, we have the statements for this data frame are these, and the questions are these. Where is Mary bathroom? Where is Daniel hallway? Okay, so next, when we split up the sentences into their tokens, we can tag them according to their part of speech. So we process that. We add this column, and we can kind of see what it's doing. So we have the word first, and then we have these tags. So this means noun, proper noun for Mary. Moved is a verb, to moved. To is a preposition, and so on. So we tag every single one of these words according to their part of speech. And actually, that's just enough to do what we need to do. Of course, if we want to generalize this, we might need to extract more information from these sentences. But it turns out to be enough for this problem domain. So I want to keep it as simple as possible so that we can explore how Neo4j can help us accomplish this task. So due to the simplicity of the data, the sentences are very simple and can be extracted into a triple: subject, relation, object. This is actually just enough information to be able to construct a graph. So I'll show you how this translates into a graph in a little bit. First, we need to extract this. So we do this based on the part of speech tags. So we have this function called extract statement. For each word and tag in our sentences, if the tag is a noun, it's the subject. If it's a verb, it's the relation. And if it's at the very end and it's a noun, then it's the object. So moving right along, we have a couple, so we have this function extract statement. So for an example, we have Mary moved to the bathroom, and then we have the triple, Mary moved to bathroom. Pretty simple, but it's quite important. And then again, we have another function called extract question that says, where is Mary? And what we want to extract is basically the object of the question, which is Mary. And likewise for other questions, John or Sandra or whoever, we just want to extract that. And very simple, we just look at the tag and say if it's a noun, then the entity under discussion is that word. So if we look at what it's actually processed into, we have Mary moved to the bathroom, turns into Mary moved to bathroom. John went to the hallway, translates into John went hallway. And like, where's Mary? Is Mary. And where's Daniel? So we've extracted all of our information, and that's just enough to get everything going. So now here I define a few debug functions just to be able to verify that our information is correct. So this function right here, person statements, if we pass in a parameter Sandra, we see get us all of the sentences that have Sandra as the subject. And we can do this for John. And we have all the sentences that have John in it. This is just to verify that when we query Neo4j that we get the answers that we want and they're indeed correct. Likewise, we can get the n most recent statements. So we have Daniel went to the garden is the very most recent sentence. And the sentence before that was Daniel traveled to the kitchen. So useful for debugging purposes. Okay, now we finally get into the Neo4j portion. Once we extract into these triples, we can actually merge them into our graph. And instead of showing you the final result of, here's the best implementation that I found that works, I want to step through the ideas so that that information is not lost. The ideas of how to construct this graph according to these very simple triples. So we're using the Python Neo4j library and just basically create a driver to our database, make sure it's running, and you have the correct credentials. Few functions here, a simple function to reset the database. So make sure that if you're running this, that all your data is either saved or you're working in an environment that doesn't have any critical data in it, because we're going to be resetting and creating a whole bunch of stuff. Here we define a helper function that basically executes some query according to a given subject relation object triple. We basically run it with our query. So first, V1, basically my first idea into creating this, and it's kind of the simplest idea, is to have this query run. So we have basically a subject node corresponding to the subjects in the sentences, an object node corresponding to the objects, and we draw an edge between every subject and relation. So if we execute this and go into our browser and look at it, it's a bit messy, so I've already kind of split it out. So here's kind of what it looks like. We have the 4 characters in this dialogue, John, Daniel, Sandra, Mary, and they draw an edge. If you can see, there's edges that say moved, journeyed. So we have a whole bunch of edges that say Mary went to the bedroom a bunch of times, Sandra went to the bedroom a bunch of times. But there's a huge problem with this graph, is that who went to what room and in what order. That's pretty important to be able to answer the questions. And all we know right now is basically, everyone went to every single room. That could be useful, but not useful for the questions that we're answering. So we need something a little bit stronger that can order these relationships together in such a way that we can find who's in the bedroom right now, or what the questions are asking, like where is Mary? Mary is everywhere according to this graph, but we need to do a little bit better. So that's the first idea. Second idea is to perhaps treat relationships as also nodes in the graph. So let's reset the database. And what's a little bit different here is that we're creating relationship not as an edge, but as a node. So we go into this. Here's what it looks like. We have our 4 characters again, Mary, John. Okay, so we have Mary moved to the office right here. And we have these edges called R0 and R1 because I'm terrible at making names. And it's just basically edges that bind these nodes together. So Mary went to the bathroom. Mary went to the bedroom. So you can see that the nodes in green are relationships that bind the subject in blue to the object in red. But again, these aren't really ordered. So what we can do is to create a linked list between all of these nodes. So that's where V3 comes in. It turns out this is just enough information to be able to answer all the questions correctly. So if you reset the database, the query is a little bit bigger, but I added comments right here that says create relationships between different relationships. We'll see what this looks like in the graph, and then I can explain what the query does. All right, so V3. Here's kind of what it looks like when you open up the graph. So we have 4 characters again. Nothing much has changed except you notice that we have these yellow arrows, these edges between these nodes, and it basically orders the sentences in relation to Mary or John, our subjects in our sentences. So we can see that the first thing that Mary did is moved to the bathroom. Next thing is Mary moved to the hallway. Next thing is Mary went to the bedroom. Until the final thing that she did was go to the office. So now that we've ordered everything according to what a person did, we can actually traverse this graph and find out everything that we need to reconstruct the information to answer the questions correctly. So where is Mary right now? It's actually the last node right here. And a small detail that I left out is there's also a head pointer so that we know that we are at the very front of the graph. So we see here Mary has this head pointer to journey to the kitchen, which means this is the very front of the list. And this head pointer will basically update every time a new relationship is created. So if we have a new sentence like Mary went to the bathroom here, then we'll create a new node here, node here, and we'll update the head pointer and make it the head of this new linked list. So I can actually show you that, what it looks like. So I have a query, yeah. Let's see. See if this works. So here's what the query looks like. We create subject and object nodes, create a relationship in green, and update this head pointer to be the newly created relation to the head of the list. And then we do a little bit of cleanup right here. Find the previous head, remove that status as the head, and update the next. It's essentially a pointer. It's an edge from vertex or from node to node. And then, yeah, we do a little bit of cleanup, and voila, we have a graph that we can traverse.
So Dan, in this model, would you ever have the case where the subject in one, I suppose one triple is the object in another one, or is that wouldn't happen as in this one?
In this data set, that doesn't happen because it's so simple. So it's basically John went to bedroom, bathroom, they're all rooms, they're disjoint from each other. But you're right, that can happen if they're named the same, and it will point to itself. I haven't actually dealt with something like that, but that's a very real possibility.
Cool, and then we've got one other question. Hang on, let me just check exactly what it says. It says, it seems like you, this is from Jeffrey, it seems like you couldn't tell if two people are in the same location at the same time. Is that correct, or would you be able to work that out?
You actually can, interestingly enough. If you look, let's see, go into this other one. This one's it. So if we look at these locations in red, if we move this out right here, we can actually find all the people that are currently in this room. So all we have to do is make sure that this is the head of the list. Because I limited it to 50, it doesn't always return the head, but let's just pretend that this is the head of the list and Mary's in the office right now. We can look for all of these relationships and find the head of John, for instance. And,
okay, and you'd be looking like if the last location of any two people is the same, then they're probably still both in the same place.
Then they must be in that room. Exactly.
Okay, that's cool.
So John is in, or actually this is the last thing that they did. So yeah, you have to traverse this to find the very first node. But I alleviated that. Instead of needing to traverse this every time and making that an order n operation. Maybe Neo4j has some optimizations under the hood, but I decided to make this explicit and say, there's this head pointer, find me the head, and basically you can match a pattern that says any subjects that have a head pointer to this object must be in that room right now.
Yeah. What was your process for evolving the model? So I guess you said on the first one, you just sort of picked what is the most obvious translation of the output from NLTK into a graph. How did you come up with the other models? Did you what made you change it? I guess you said you couldn't write the query you wanted to for one of them.
It's a lot of just a process of discovery, I guess.
Okay.
It's very much a creative process. I'm sure that you could have invented a totally different way. For instance, make Mary not even bother using a graph and just have all the properties inside Mary. But I found that this is a bit too basically a relational database, and it's harder to manage. So instead of pulling them out into these nodes, it paints a really clear picture as to what answer you're getting after. And also, you can traverse the graph pretty easily, and Neo4j has some really nice mechanisms for doing that. So it's very much error and trying to figure out, okay, what's the thing that we need to get at, and how can we organize this data structure in a way that is extensible and gets at what we need to do.
Cool. Yeah, I mean, the final solution is looks pretty nice. It seems like it seems flexible enough to allow you to answer lots of different questions, even more than the ones you initially had.
And that's exactly why I went this route. Is interestingly enough, it also is able to answer the next task. I can give you a sneak peek. as to how it looks like. Let's look at that data frame. Do I not have it?
Cool. Sorry, I didn't mean to ruin your flow. You can
yeah, that's okay. We'll get to it. But it works with a whole bunch of other different ways of looking at the problem. So the way it works is that it's generalized essentially to any statement of the form subject relation to object. And the rest of these 20 tasks basically follow that format. And by ordering these relationships in this way, we can actually simply just traverse the graph in a different way to find the answer that we're looking for. I also made the deliberate decision to not put any meaning into the graph itself. So in other words, there are no semantics in the graph other than, that could be a discussion for another day. But what I really want to get at is to essentially only put the syntax in the graph. So this only captures the structure of the data. So John went to the garden, John went to the office, and so. So only captures really the syntax of the sentences and the order in which they're put in. But it doesn't really say anything about what that means. The way you get meaning from that is to traverse the graph. So if you want to find the meaning of what person's in what room, you construct the query in such a way that you traverse it and associate this subject to this object and say, when a person is in a room, they're in that room. So that's also another decision I made that was the reason why I came up with this. So it's a really nice way of visualizing the data, quite interpretable, and it works quite well. So let's actually evaluate this data. So we can query the graph. Here we have a simple match that says, like we have before, find the subject that is at the head of the list that we have created and return it. And if we input, oh no, I think I didn't run something. Yep. Let's reset this. It'll take to run through everything. All right. And then let's run this again. Okay, so we run the query on the graph, find the person, Mary, basically which room is Mary in, and it gives us the answer kitchen. And this is directly from Neo4j. It basically issued a query on Neo4j. It didn't do any cheating or look at the data itself. So if we look at what the answer should be, because we created these debug functions that I mentioned earlier, we have this data frame. And indeed, the last recent statement pertains to Mary journey to the kitchen. So we know that we're on the right track. As we can find the last n rooms that a person has been in. There's a little bit more complicated query here. This is basically traversing the most recent relationships and then basically collecting them down at the bottom into this nice list. So if we find out what it looks like, find the person history of John. So it's ordered in reverse chronological order. First, the most recent thing John did is he went to the bedroom. Next most recent thing is he went to the garden. So because it's ordered in this very nice fashion, like this. We just traverse these nodes and then collect these answers as we go along. So it's quite nice in that way. And I found it pretty easy to set up with Neo4j. So that's a huge plus. So we can also find out bonus questions that the original data set never really asked us, but I found that this is also pretty cool, is that it's very extensible. You can find information here that basically you can plug into and find pretty easily. So here we have a function that says find has been visited. Here is the office. It's been visited 334 times in our data set. And that's just by counting all the relationships that point to the office. All right, so finally, we're going to evaluate the data and calculate an accuracy score. So here's what our original data looks like if you forget, running off to the bathroom. We extract the tags, part of speech tags, into these triples. And then we simply run, if it's a statement, then we run this V3 query that I showed above. This thing. So for each statement, basically merge it with the graph. And then if it's a question, issue the query up here. And by doing that, we define that function. So here's one thing that I want to point out that I got hung up on, and I'm pretty sure that another beginner working with Neo4j and natural language processing might come across this, so I'll point this out, is that if you consume the result, basically call consume or single in the Python driver, then you can notice a very slow updating of the graph database. Essentially what this does is it returns the result back, and for this data you don't want to do that. It slows down the results considerably, because once you issue a query, now you're waiting for the results to come back and then issuing the next query. Instead, what you should be doing is to issue all the queries immediately and then wait for all the results to come back afterwards. So basically you're batching up all the queries together and only waiting for the results to come back, execute all the queries. Otherwise, it might take much, much longer than you anticipated. So that's something to watch out for if you're doing any kind of processing. Don't wait for the result. Don't wait for each result to come back. Do it at the very end. So finally, set the database, then start the session, get our results by executing this function, get answers. Find an array of our predicted and our actual results and compare them. So it'll take about 10 seconds for that to run. That's about 10,000 statements, I believe. So if we look at the first 5 results, here's what we predicted from our graph that we constructed from each of our questions. And here is the actual results here from our data frame that we were basically given, because this is a supervised learning task. And if we calculate the accuracy score, it's 100%. And that shouldn't be a surprise. That is usually unheard of, but since we're working with such simple data, we don't need to worry about it. So that's the very first QA1 task in a nutshell. So do we have any additional questions?
Yeah, we got a couple. Let me just summarize them. So first one was, well, the latest one is from Jeffries, roughly saying, just going back to our conversation about whether you can tell people are in the same room. So I think we discussed that you could tell if people were in the same room if they're there, if the last place they are is the same room, but you wouldn't be able to tell if they were there at some time in the past, unless you put some sort of notion of time, I guess, onto the visits to the rooms. Is that right?
Since they're ordered, well, actually, you're right. In this graph, you can't, because it's relative to a person right here. They're disjoint from each other. Notice that they're not globally ordered. They're ordered according to John, Sandra, Mary, Daniel. So you can't really tell between them what is going on. But actually, that plays really nicely into the next task, which is an iteration on this idea, which basically introduces the idea of globally ordering all of these. And not only that, ordering them according to the objects as well. So here it looks a little bit messy, but I'll walk you through it. So we have ordered list right here in yellow, like that we added. In blue is the list of events that pertain to a single person. So if you look at Mary and just look at where it tracks along right here, we can see that Mary first went to the bathroom, then Mary went to the, picked up a football, went to the kitchen, went to the garden. And if we look at just kitchen in red, we see that the first person to interact with the kitchen is John, then Mary. So it's relative to the object as well in the sentence. So not only do we have an ordered list of all the places that a person has been or objects that they have interacted with, we also have an ordered list of that happened to an object like the kitchen, or here we have a slightly different data set. So I'll go into that. Well, actually, do we have another question, or?
The only other one was about, like, I think it's more about an extension that you could add to this. Could you add, categorize the nouns and verbs? So, for example, pull apart people, things, different types of verbs, so moving or taking, putting, using, and maybe capturing emotional responses and that type of thing. I guess it's not, I don't think you've got that in there at the moment. Is that something that you would think could be useful to add, or?
Yes, I think so. Right now, the goal is to move all of the semantic information about the relationships between things out of the graph, so that we can just simply say the meaning of the graph is associated within the traversal of the graph, and like what some kind of I don't know, the relationships between objects and people. So in this graph, we have a football, which wasn't there before. And basically, we're trying to find out where these objects have been picked up and placed. But we don't encode any information between what the football has in with the kitchen, for example.
Okay.
Some implicit meaning in the dialogue that's not given explicitly, that the football can be in one of these rooms. And we can actually traverse the graph to find the answer. But the meaning is in how we traverse the graph and what information we extract from that. But you could very well just say, I'm not going to do that. I'm going to actually put in information that added afterwards that says, maybe I can add a pointer that says this football is in the kitchen and have an explicit relationship between them, or add other information related to that. But I want to get to the bare essentials. That's what I'm trying to do, is using only the information from and turn it into a graph,
Yeah.
how can we traverse this? That's the approach that I've taken. But of course, you can make it as complicated, easy, or hard as you want it. So that's kind of my approach.
Cool.
So is that?
Yeah, I think that probably explains it. By the way, we've probably got about 10 minutes left. So I don't know whether we want to continue going through the notebooks, or maybe you want to show the product that you've been working on to wrap up.
Okay, so I'll briefly go over this notebook. So I kind of detailed as to what it does. Let's just run over this. The very first steps are very similar. We just import a new data set.
So is this now a different data set than the Facebook one, or is it still a?
They have multiple tasks. So this is QA1.
Oh, okay, so it's still part of the same thing.
But the data looks a little bit different. So let's see if we can look into it. Data, the first 10. So here's what it looks like. Mary moved to the bathroom, moved to the bedroom. Mary got the football there. John went to the kitchen. Mary went back to the kitchen. Mary went back to the garden. Where is the football? So here immediately we see something different, is that there's be picked up by people and moved between rooms. So how can we figure out this? So we do something very similar, part of speak tag, extract the triples. In fact, we don't need to alter the graph in terms of syntax very much. We just define these new relationships. So let's go into it.
Yeah.
So there's this, it looks a bit massive query, but it's not that bad. We just added 2 extra things. Basically, what we have here, just an extra list, more pointers that point in this linked list of events relative to subjects or objects. Build it. There are some. All right, build a graph. Takes a little bit longer, maybe like 15 seconds.
I guess there's more data in this one, is there? Or is it just more complicated structure?
It's the same data, but we're actually doing more in the query.
Oh, wow, it's quite a query.
Usually it doesn't take this long. Okay. So we traverse the data. Oh, okay. Let's just evaluate the data. That's all we have time for. So internally, what it does is it looks this query. Let's see right here. Find object location. Basically traverses the graph, last 20 things, last 20 relationships, and finds the let's see. Yeah, finds the object like a football and kitchen. So I've explicitly defined this in some other array that says kitchen and garden and rooms are different from objects like football. Fitting between them outside of the query, we can import them in the query that says if it's not one of these, then it must be an object. And we can traverse the graph and associate, okay, if John is in the kitchen right now, then we traverse this backwards and find the most recent object that John picked up, and we can basically look backwards and find the answer that we're looking for. That's the gist of what it's doing. And that's just enough information to be able to answer every question. The queries do get quite a bit more complicated, as you can see. It's pretty long. You can shorten that a lot if you encode those relationships in the graph explicitly. But I just wanted to make it as simple as possible graph-wise. And we get an accuracy of 100% again. If you have any additional questions, I'll be happy to answer on the GitHub page. Just open an issue. I can also explain a little bit more, but we're running out of time, so that's what I have to say about this. There's also a third task right here. It's a bit different. Don't have time to go into it, but I'll be happy to answer any questions you have about it if you're running through it. And the data set I was using is on the Facebook research page, the BIB project, and you can find it there. All right, so let's get into finally what I'm working on. All right, so here's kind of what the interface looks like. So I'm the sole dev of this project, and
you make it a bit bigger, Dan. It's still a bit on the left-hand side of the screen.
Is this better?
Yep.
All right. So let's see if we can sign out. So here's what the interface looks like. It's a web interface right now, hoping to move into a mobile app. And basically, I click this and sign in. This interface pops up. It's basically like a chat bot. We decided to create our own front-end interface because we want to experiment with different ways of showing the UI. For example, what if we want to show a graph of the relationships of what we're doing? So actually, I'll hold on that for a moment. I'll show you how it works and then explain a little bit more about that. So hello, my name is Augie. I'm here to help you organize and remember things about your daily life. Click the button below to get started. Okay, first I'd like to get to know you better. What's your name? My name is Dan. And what's your last name? Kondratyuk. So if I click this open, fantastic. I can now display this information whenever you ask. Here's what it looks like. So if I ask the system again, what would you like to find? I'd like to find a person with, last name Kondratyuk. I will pull up every person that it's found. So we have first name. Here's kind of what it looks like. So let's tell it about something else. I know another person named Dan. What do you remember most about this person? He's my friend. And what's their first name? He's also Dan. And what's their last name? I don't know. Cannon. What's their email? So you can skip these dialog options and basically restart. And let's ask, okay, what would you like to find? I'd like to find a person. And if I find Dan, if I ask for Dan, so basically it finds, well, that's a bug right there. So it should be two people, I guess. And it should have showed, gotta hunt it down. So
the two Dans are merged together.
Yeah, as you can see, I have a little bit of work to do, but the intent is for two different people to show up, and it basically shows you a list of all the people related to that. Internally, it uses Neo4j to create all these relationships together. So if we also created a tag, what we call a tag grammar, it's basically, you can also search by hashtags. So Dan returns back the results, what we have, but we can also say, that's another person, first name of, Bill, and a last name of, Cannon as well. Okay, so if we search for Tannin, hopefully, so it'll show both of the people that are basically with the last name of Tannen. So the goal is to create, internally it creates this graph of relationships between people and companies and events and stuff like that. So if we go back to question answer and restart this, just basically ask it about a whole bunch of different stuff. Provided that you put the information in there in the first place, you'll be able to find whatever you want. And if you forget about something, that's okay. If it's related to anything else that you put in, you'll be able to find it that way. So it creates this huge interconnected graph of all these people and companies that you worked at or know about, events that you've been to. Much easier to find information that you might have forgotten. So that's the gist of what I'm working on. Worked on it for the past few months, tracking right along and experimenting with different ways of organizing the user interface to make it more, make it easier to use. For instance, what if we show a graph right here and then you can click on it and zoom into it? Of course, it'll have to be a lot simpler than what we have in Neo4j because there's tons more relationships. There's a lot of really cool research questions about how we can organize this in such a way to make it very intuitive. So that's kind of what I'm working on.
Cool. It looks really good.
And
I guess
so,
we've reached 6 o'clock, so we'll probably wrap up there. So
right.
Thanks everyone for joining us, and thanks Dan for taking the time out to show us what you've been doing.
No problem.
Next one of these meetups is actually next Wednesday. So we've got Nigel Small from the drivers team is going to be talking about the Bolt protocols. That's a new way of interacting from Neo4j drivers with the Neo4j server that's been there since 3.0. And then in the future, probably sometime in August, we'll do another one where we get a few drivers authors together to talk about how they went about implementing those. Otherwise, enjoy the rest of your day. Thanks, and thanks to Dan again. Bye.
Thank you.